Oh, well, it's the skull, and it's like the definition of the saying you get it.
It's the most recent.
Oh,
Anyways, you guys use.
yeah, I know. I think part of the five would probably. So from that seven.
Oh.
All right. So we ended higher order equations. So turns out that higher order equations are not that scary because it's the same idea as second order equations. You just build the characteristic equation. The pattern is still the same. Your x triple prime becomes r cubed. Your x to the fifth derivative becomes r to the 5. You're going to have a harder equation to solve. Like if you have a fifth degree characteristic polynomial, you'll have 5 up to multiplicity roots up to multiplicity 5. Like this only had plus or minus I and 0, but 0 counted as 3 roots because it was a triple root. And we noticed that every single time you have like a double root, for instance, you would end up like multiplying by t. But if you had a triple root, you would multiply by another t, and you just keep multiplying by t to each additional. The summary is like this stuff right here. So this is just saying like you would multiply a root of multiplicity m like t successively until you've run out of all the multiplicities. The original one doesn't get multiplied by t. And then the complex case, you'd also do the same thing. You copy your original, and then you copy it again. You'll copy your original and then multiply it by t as many times as the number of multiplicities of your complex conjugate root. This was an example where we had that. So that's higher order. But all of these equations we've done have always had constant coefficients. So like all the coefficients in front of the x double prime, x triple prime, x quadruple prime, any of these x and its derivative terms, which we typically put on the right and on the left, and then everything else on the right, have always had constant coefficients. So they've always been of this form where your a and your b and your c are all constants. But you may want, we're going to generalize this to be non-constant necessarily. So let's see if it's gonna, what is going on? Yes, good. So I'll just say so far, they've all been constant coefficients. So we've assumed that this A and this B and the C that are in front of these guys are all constants. But what if you were to say that let's keep A and B and C and all those constants, but what if they're now instead of constant, they're non-constant. So if let's say we just introduce this additional t squared here and then a t here. Okay, so I mean, in general, you could do even, more than that. You could have something that's more complicated than that. Like you might have, I don't know, like if you had, for instance, a ln of t over sine of t or something ridiculous. X double prime plus, I don't know, b square root of t times e to the t x prime plus c times 1 over, or I guess I could do c over t times x is equal to 0. Of course, this is way harder, but I'm just pointing out that what's new about this is that we have a variable t that we've introduced as part of the coefficient that we normally never had. We've only just had a simple number. And so, in general, you could have some ridiculous, function for t, like something more complicated like this. But let's start easy and just have a t squared here and a t here, and let's not even have anything here. And here a and b and c are still constants. So this specific type of equation is a non-constant coefficient linear. It's still linear. What makes it linear is that the x's are to a power of 1. So your t is a squared here. That's still okay. What makes it linear is the x. It's all about the x, the unknown, the solution variable x, and its derivatives have to appear as a linear polynomial. So if this x was a squared here, that would be making a nonlinear differential equation. But you're allowed to do whatever you want on the independent variable t. So your t could be squared. In fact, this equation down here that I just randomly wrote is also still linear because the x's and its derivatives are only to a power of 1. Although t doesn't appear linearly, all the t's are nonlinear functions. Like sine of t is not linear, ln of t is not linear, e of t is not linear, square root of t. But so t squared is not linear, but linear to a power 1, but it's not about the t, it's about the x that makes it linear. So this is still a linear differential equation, second order because x double prime, but it's non-constant coefficient, but it has a specific form where on purpose, we're introducing a non-constant coefficient differential equation where the t squared and the x double prime, and then technically this is like t to the 1 and x prime. And then you could think of this term right here as no derivative. So then I guess you could have like here, you could think of it as there's a t raised to the 0, which is equal to 1. So you don't have to write that. So what we're doing here is we're introducing t to the power that's equivalent to the derivative of that term. So this is an x double prime, we put a t squared. This is an x prime, we put a t to the 1. And this is an x without any derivative, so we put t with no derivative is to the 0. This is called an equidimensional differential equation, or people also call it a Cauchy-Euler. I guess the book likes to just condense it and just call it Euler. So this is a second order non-constant differential equation of the form that falls under this structure. And I'll just underline the power that matches the order of the term's derivative. It's a variable t to the power that matches the order of the term's derivative. So in general, you could have like a ridiculous equation like this with the t's being some very, very complicated or more complicated form, but and those would be harder to solve. This one, though, is like easier to solve when it's got this structure to it where it's like equidimensional, where you have like the power of the t that's there is the order of the derivative on that term. We're going to look at this with a homogeneous for now. So, of course, this is homogeneous. This is for now, though, we'll relax this and look at non-homogeneous. And of course, these are not constant anymore. So what's the correct solution form for this so-called Euler equation? Well, what did we used to do? Let's go back and review how did we do it when we had constant coefficients. So this a, b, and c were all constants. We ended up noticing that we could plug in a certain type of solution form. What do you guys remember what it was? It was like CE to the RT. We did this, right? So we said like, let's go back. So when we were looking at second order, here we go. So we propose that CE to the RT. I mean, the book talks about the fact that this E to the RT is a good form. The way we motivated it was this one, remember, we could do separation of variables. So like this was a first order equation. In the end, it always was the homogeneous solution to a first order equation was you just read off what's in front of the x right here and then do CE to the negative of that. But had we thought and this -4 shows up because there's a +4. But what if we just said, well, the form looks like CE to the RT. If we plug it in, we'll find that R is equal to -4. So it's consistent with what we saw. But this right here, you could have done by separation of variables. We took that and said, well, basically we're just adding a second derivative term. Why don't we try the same solution form? So like first order equations, we noticed that it would be like CE to the something t, and that something ended up being the negative of what's in front of this x. For second order, we just said, what if we just say it's also going to be CE to the RT? And we'll force this thing, we'll try to find the R that'll force this thing to satisfy this differential equation. And turns out that the R that you would need is going to have to satisfy this characteristic equation. And you'll have in general up to 2, 2 up to multiplicity. And then you just add those two together. And this wasn't that surprising because if you plug this in, the nice thing about an exponential is that its derivative will be itself. And so every single term, x double prime, x prime, and x will contain e to the RT. And then there's hope that you can get them all to undo each other because they're literally all the same. And you just have to like tune the coefficients in front of them in such a way that you magically can get all of them to eliminate each other. And it turns out that that's going to have to satisfy this. So that's what we used to do. We're just trying to review like what did we used to do and then try to see if we can build on that intuition to do this Euler equation. So what do we used to do? We used to say we plugged in this to get the characteristic equation. AR squared plus BR plus C has to equal 0. And then we would solve for the R, right? That's what we ended up. And then we ended up having distinct roots or repeated roots or complex roots. So that's just a review for what we did back then. So turns out that this solution form, this x is equal to, so in general, x is equal to CE to the RT will not work for this one. So you can't just say, I'm going to just plug this in and then hope to get some kind of some other version of a characteristic equation that will work. The reason why this plugging in will not work is because, like I said, the derivative of an exponential is itself. So if you plugged CE to the RT into this differential equation, your x, this term is going to have an e to the RT because it's just plugging it in directly. This x prime term will also have e to the RT with with actually like an R that pops out in the front because of the chain rule. But it will still have an e to the RT. And then this x double prime will also have an e to the RT. But the issue is that this is multiplied by t. So this term will be like t e to the RT. This will be t squared e to the RT. And this will be just e to the RT by itself. That won't have hope of canceling them each other. This up here was okay because this would have be e to the RT. This would be only e to the RT with some constant. This would be some e to the RT with some constant multiplied to it. And then we just have to figure what constants that would have to be in order for this solution form to be forced to satisfy this differential equation. But there's no hope that this will work out because all the terms will have some kind of, they're multiplied by t and t squared. And of course, if you wanted to solve the differential equation when t is equal to 0, then you're good, but you wouldn't have a way to get all the terms on the left-hand side to eliminate for all t, like for all t, like I'll just circle that right here. So we want to have a solution that isn't just for when t is equal to 0, for all t. So this solution form, even if you try to, you can try it on your own, plug it in. There's a little, just not that much work to show that, but you'll see that there's no way you can find an R, for instance, that would satisfy this for all t. So what we're going to do is we're going to propose something different for the solution form. It's probably hard for you to be able to look at this immediately and it's not that much of a stretch once I tell you what it is, but you might be able to see this without me telling you, but I guess I'll just give it to you. We're going to say instead of CE to the RT, the solution form that I think would be reasonable for this would be C to the TR. You see how this is different though, so I'll say this is not CE to the RT. So this is just T to the R, not E to the RT. And I'm going to justify why this is a good form for this. The idea is you want to make all the terms on the left-hand side end up being like similar to each other so that they can cancel each other out. So when you take the derivative of this, of course, you're taking the derivative with respect to t. So t is your variable, so you're going to pull the r down, and then it'll be t minus 1. R is just a constant. And then you have x double prime is c, and then you pull the r minus 1 down, so it'll be r times r minus 1, t r minus 2. That will be the second derivative. So why does this solution form make sense? What I'm going to point out here is, of course, when you plug in this solution into this differential equation, I've already taken all the derivatives, so all I'm just going to do is plug it in. We're going to have a good idea of like why. So this x, I'll just say that it's going to be like a term that has t to the r. I mean, there's a c here. I'll make this a capital C so that it's different from this little c. But I'm just going to say this is going to be kind of like I'll do a little, this squiggly just means that it's going to be like a t to the r term with some constants in the front. But the idea is I want all these terms to have some constant times something that's the same. And then x prime, remember c and r are constants. C is like an arbitrary constant. R is probably a constant that you want to find that will force this thing to satisfy. But in general, this is going to be like a t to the r minus 1 term. So I'll just say like this x prime term is going to be like a t to the r minus 1. And then your x double prime term will be like a bunch of constants that are multiplied in the front here, but it's a t to the r minus 2 here. So this x double prime will be like something like a t to the r minus 2. But if you look at this, if you have a t to the r minus 1 term that's being multiplied by a t, this together, t times a t to raise to the r minus 1 becomes a what? What do you do to the exponents? You add them, so it becomes 1 plus r. This would become like a t to the. What is 1 plus r minus 1? R. Just be like a t to the r. What about these two combined? You have t squared times t to the r minus 2 would also be a t to the r. So we have now 3 terms that are going to all be like t to the r times some constant. So they're all going to have the same form. And there's hope that we can actually get them to eliminate each other now. You can't get like a t squared e to the rt to eliminate a t e to the rt, or t squared e to the rt to eliminate a t e to the rt. If you can get all of them to be the same up to a constant, then you can just try to find the constant that would end up making all these eliminate each other. So that's the motivation, is that the equidimensional is a very special type of equation that allows us to use this differential equation, this solution form, where whenever we take successive derivatives, because of the power rule, the exponent goes down by 1 or 2, but we're compensating for that by multiplying by t squared or t, so that if we did plug this solution form into this, every single term will become a t to the r term, and then there's hope of trying to get all of those to cancel each other to equal 0. So that's the intuition for why this solution form will not work anymore, because it doesn't have that property where you're going to get all the terms to actually be the same. But this solution form would actually work. So in the end, your solution form that you're going to use is going to be like this. So why don't we see what kind of, there's going to be like a characteristic equation for this type of problem as well. So let's just go through and do that. So let's say, okay, the idea is that the solution form will be of this type, t to the r. And then, of course, in general, there will be like a c in front of here, just saying that you have a, or C1 or C2 if there's like multiple. So we'll see that in a moment. But the idea is that it captures, the book writes it like this, and I think it's good to write it like this because they like to, I mean, they don't talk about linear algebra a lot, but this will be like your the basis of your solution space would be of this form, and then linear combinations of that would be the span of the, yeah, C is like gonna be like your arbitrary constant. It could be whatever you want. And then R is the one that we're gonna find that has to be something in order for it to satisfy this differential equation. Similar to like what we had for this constant coefficient one, CE to the RT was the solution form. And then R was the thing that we needed to make sure was equal to something. And then in the end, the general solution was like C1 e to the one of them plus C2 e to the other one. And the C1 and C2 are like your arbitrary coefficients. So let's just copy this stuff here because we just did this right here. So we could just reuse this right here. So the idea is we're going to say this is the new solution form, not the e to the RT. And then we have all this. What was the differential equation? The differential equation this time is a t squared x double prime plus bt x prime plus cx is equal to 0. It's easy to remember this because it's just the same as ax double prime bx prime plus cx, but I just put a t that's of the same order power as the order of that derivative, and then we just plug it in. We know that there should be a way to get all the terms probably to cancel each other out, but we want to find what condition needs to be, what condition on R we need to have in order for that to happen. So you have a t squared. The x double prime is this term right here, the CR, this thing. So I'll just make it a very capital C, R minus 1, T, R minus 2. That's x double prime plus BT. X prime is this right here. So I'll just say capital C, R, T to the R minus 1. And then the last term is a little c. Just make it clear that this is a little c, and then this capital C, t to the r, is equal to 0. And then you'll see that there is, so the idea is, like we said before, you can combine this t squared and this t r to the minus 2, this t and this r minus 1, those all combine so that you'll get a c r minus 1. And then, of course, this t squared and this t r to the r minus 2, we already said combines to t to the r because you just add. And then you have plus b c cr, but this t and this tr to the minus 1, they combine to t to the r. Plus little c, capital C, t to the r. And that was the point, was now you got all these terms have t to the r in them. So you can actually factor that out. So you'll get, and you can also factor out the capital C. So I'll just say capital C. You have the t to the r that's common across all of them. And then what are you left with? You're left with a times r, it's just a times r minus 1 plus b r plus, I pulled out a big C, but there's little c still is there, is equal to 0. And last time we said this as well, we want to have that c is not equal to 0 for non-trivial solutions. So if you plot there, so how can you make this equal to 0? There, a variety of ways. Of course, if you make c equal to 0, then of course this all goes to 0. But that would have been as if you just said c was equal to 0 here, which means that you're just saying your solution is 0. And the 0 solution will satisfy this because x equal to 0 is 0, x prime of 0 is 0, x 0, x being 0 double prime is also 0, so to be 0 equals 0, so 0 is fine. That's only one of the solutions. We need the general solution, and it's actually called a trivial solution, and that trivial solution will always satisfy any homogeneous differential equation. The other way is to make this t equal to 0, but that's like saying, oh, we are going to just be able to satisfy this differential equation just when t is equal to 0. We want to be able to find a solution that would solve this differential equation for all t, not just when t is equal to 0. And so that leaves us with only one other option, is to make whatever the heck is in here equal to 0. And so we don't want c to equal 0 because that will give you your not a trivial solution. That's your 0 solution. You don't want this t to be necessarily 0 because then it's like saying you're only able to solve this differential equation when t is equal to 0 and not for all t. So then if you wanted to satisfy it in general, you need to have this has to equal 0. This is going to be like our characteristic equation we had before. So you'll have like all of this that's in here. Is equal to 0. And it's going to be a quadratic equation if you multiply everything out, because this is an r squared term, this is an r term, so the highest is going to be an r squared. So it's still it's still a quadratic equation, and it is like an equation for r, and we're going to have to find what r satisfies this, and that'll be the roots of this, and the solution will be ct to the r. So our solution form is different than what we had before, but it will still have a similar pattern where you find the r and then you'll put that r into the r right here. And people actually have a different name for this just to distinguish it. It's like a characteristic equation, but people call this the indicial equation instead, just to make a distinction between the characteristic equation was what we saw before, and then this is like for this specific type of equation, this Euler equation, you'll have an indicial equation of this form that has to be satisfied. That'll force this solution form to solve the differential equation. But this is a quadratic equation, so you'll have all those cases we saw before. So the first case is distinct real roots. I'll just copy the initial equation. So I'll just say this is my initial equation. This is my initial equation. So if we wanted to solve this differential equation, from reading from this equation, okay, so I'll just say this is your general. This is the initial equation that you'll get if you had an Euler equation that's of this form. So it's clear here that A is equal to 2, that B is equal to 7, and C is equal to -3. So your initial equation will be 2r, r minus 1, plus 7r, minus 3 is equal to 0. And you can multiply all this out. This is going to be 2r squared. Minus 2, but plus 7, so it's going to be plus 5r. And then you'll have a minus 3 equal to 0. And then you can factor this. So if you factor this, you'll end up getting 2r minus 1 and then r plus 3, which gives us that r is equal to half and -3. Two distinct real. Your solution will end up being, one of them is C1, t to the 1/2. It's not e to the, half t. It's t to the 1/2 because our solution form looks like this now. It looks like c to e t to the r. So that means that one of them will be this, and the other one will be C2. I'm so used to writing e to the -3. Okay, because our solution form is now different. Yes.
Because the C1 and C2 are arbitrary, you have to write C1
You want to write C1 and C2 for the general solution because you're trying to capture all the possible family of solutions. And so if you drop the C1 and C2, it looks like you got one of them, where you've got t to the half and t to the -3. But if this would work, this is the general solution in the sense that you could plug in anything for C1 and C2. You could plug in -5 or square root of 7 or whatever, and they would all satisfy this differential equation. So the general solution is trying to capture the infinite family of solutions. And for second order equation, there'll be two arbitrary constants that you can make anything be anything, and it'll still satisfy the differential equation. Yes.
Is that initial equation true for second order Euler equations? It's just the specific.
You mean this initial equation here?
Yeah.
Yeah, this initial equation will always be for all equidimensional or Euler equation where you have a t squared and a t in front of the x double prime and x prime respectively. Anything of this form. And we know that because we did all the work here without ever, we kept everything general. Like here, A and B and C said we could be anything really. And we still got that the result had to be this. But you do definitely need the t squared in front of the x double prime and the t in front of the x prime to get this to, yeah.
So then our general solution now becomes homogeneous.
This is just a homogeneous, yeah, we're only looking at homogeneous Euler. We will be able to do a non-homogeneous Euler after this. So we always try to do the easier problem first. If this 0 here on the right-hand side was not 0, then we'll have to do something more. You still do probably like we did before, and this is always is still the case in this problem as well. You'd still compute the homogeneous solution, and then you'll propose a particular solution. Actually, it turns out that you can't even use the method of undetermined coefficients when it's not constant coefficients in front of these. So we'll have to learn a different method that uses some more. It ends up becoming like solving a system of equations, and we'll make it easier by using some linear algebra. But yeah. So we're just looking at our first example of a non-constant coefficient by just putting another like term instead of just A, B, and C. We're putting a t-dependent term, t squared and t, but it's very special because it's equidimensional where it's like the t squared and the x double prime and t and the x prime. And then it's really just going to be this initial equation. But remember that our solution form is now t raised to the r, c t raised to the r. So we have to use that instead of the other one, which is the e raised to the rt. We can't use that anymore because we didn't use that. And I wrote here t has to be greater than 0 because our solution here has t to the half, and we want that we want the t to so I'll just make a note here that this implies that we probably want t to be greater than 0. I guess this implies that we don't want t to be 0. So t greater than 0 will just like, actually this is okay to be equal to 0, but the combination of these two implies that we want to have t greater than 0. We could look at the case when t is less than 0. The book doesn't do that. There's actually a general solution that would work for all t, probably not when t is equal to 0. it turns out that you just put absolute values on these t. So it'd be absolute value of raised to the half and absolute value raised to -3. But it's not like that critical that I go to that case. It doesn't bring that much extra to the ideas behind this non-constant coefficient differential equation. And there's so many other things that, worth covering that we'll just look at the case when t is greater than 0, the general solution for when t is greater than 0. There is a way to write it for what it just absolute values on these t for when t is less than 0. But the book doesn't do it either. So I'll just write these things in so people are not confused, like how is my solution going to be valid for all t? Turns out that the way it's written right now would only be valid for t greater than 0. And I'm just going to sweep that away by just saying I'm just wanting you to find it for t greater than 0. So that's it for the distinct real roots. So if you look at a Euler equation and then you use the initial equation and you find that there are two distinct real roots, then you just do C1t to the one of them plus C2t to the other root. Now, let's look at one where you're going to have, like, this is just going to boil down to all the cases we saw before. What is the initial equation? The initial equation is going to be r minus 1 plus br. You might, start getting used to this and memorizing this, but of course, you can always write this on your formula sheet. So for this one, your a is 1, so it's going to be r minus 1. This is b is 3, so 3r, and this is 5 for the c. And then if you just multiply out these things, you get r squared plus 2r plus 5 is equal to 0. It's in generally going to be a quadratic. And then you'll end up getting that r can't factor nicely. So we'll just use the quadratic. So negative b plus or minus b squared is 4 minus 4ac all over 2a is just 2. And this ends up equaling -1 for the real part because -2. And then 4 minus 20 is -16. Inside of this is going to become 4i divided by 2. So it's going to be plus or minus 2i. So this is a case where your initial equation gave you complex roots. Let's find, so the idea is from the same as before. You just have two complex roots, so your solution is going to equal C1t raised to one of them, which is going to be the -1 plus 2i, plus C2t to the other one, which is -1 minus 2i. But this is your complex solution. We want to be able to write the general real solution. And so eventually we're going to use Euler's formula, which I'll just write on top here. So we did this last time too. So we get this, the idea of the Euler's formula is that you're able to take a complex exponential and split it into the real and imaginary parts. So before we apply Euler's formula, we can't apply Euler's formula right away. It's a little harder than before because before we already had e to the something for all of our solutions, but now it's t to the something. So we don't get to use the Euler's formula immediately. We're going to do a little bit of a trick to get Euler's formula to apply onto this. One thing I'm going to notice is that since this is t raised to -1 plus 2i, the idea is you can split the exponentials. So you can say C1t to the -1 and then t to the 2i plus C2 t to the -1 t to the -2i. Let me just move this down. And then once I do that, I can pull out this t to the -1. That's common across both of these. So then inside of this parentheses, we have C1 t to the 2i plus C2 t to the -2i. And then I need to get this to look like an exponential because I want to use Euler's formula. So this is like cheating a bit, but I can get any expression that I want to become an exponential. I can always do this. I can say C1 e to the ln of t to the 2I. So the idea is like I just take the ln of t to the 2I, but undo it by doing the exponential, right? And so this e to the ln of t to the 2I is the same as just t to the 2I because e and the ln's are inverses of each other. Same idea with this right here, e to the ln of t raised to the negative 2I. So only reason I'm doing that is because I got this Euler's formula that's converting exponential, complex exponential to its real imaginary parts. I just want to be able to apply that, but I can't if it's not an exponential. So I'm going to force this to become an exponential by just doing e to the ln of whatever. The log property says that you can pull this exponential, this exponent on this t out in the front. So you could pull this out. So that prevents us from having a bunch of layers of powers. So this means that it'll be t to the minus 1, c1e to the 2I ln of t, once you pull this in the front, plus c2 e to the negative 2I ln of t. Okay. So now I have it in this exponential form, so it's possible to use Euler's formula. The form of this is so similar from what we did before that I am going to jump and just use what we saw back then. It's right here. So what did we see back then? We had c e to the 3it plus c2 e to the negative 3it. Eventually became c1 cosine of 3t plus c2 sine of 3t. Or actually, maybe we'll go to the general version down here. No, we're okay with we're okay with this version. This version is fine. So what did that end up becoming? If you had, so here, this green box, apparently I wrote this here, so it's useful. You have a c1 e to the I theta plus c2 e to the negative I theta. For this problem right here, our theta was 3t because it's 3it. And so I theta will equal 3it if theta was equal to 3t. And then the conclusion was that you can do all this work, but you'll end up getting that you can rewrite this to c1 cosine of theta plus c2 sine of theta. That's all this, using even in odd properties of sine and cosine. We also redefine coefficients. So we define the c1 and c2 added together was a new c1, and then this whole I c1 minus c2 as our new c2. Because this is an I here, we said our c1 and c2 can in general be complex, but our punchline was that in the end, this ends up being what ends up happening. So I'm just going to copy that and reuse that result down here. You could do all the work that we did before and just keep in mind that sines and cosines and sines are even and odd functions. But this is the formula that we had before. So it should work the same way. This thing right here will become, so what's theta here from this interpretation? It's not just natural log t, it's got another term too, 2 natural log t. So using the same, it's going to be like in that previous one, it was like 3t in this one, it's 2 ln of t. I've literally been doing the exact same steps as we just did in that previous page, but with 2 ln of t's in place of where 3t used to be. And that might be a good exercise to have shown you guys, but I'm noticing that we're running out of semester. So I want to abridge this so we can move into other things. So you're gonna have C1 cosine of 2 ln of t plus C2 sine of 2 ln of t, where 2 ln of t is in place of what used to be 3t in the past. Yes.
Is there no I?
There is no I, but the C2 has an I hidden in it. Remember, we redefined the C2 to a new C2. And so in general, your C1 and C2 could be elements of a complex number. The idea is now that we've extracted the real and imaginary parts, that we have a way to control this to become just purely real. And so in the end, we now have our solution is going to be t to the minus 1 times C1 cosine of 2 ln of t plus C2 sine of 2 ln of t. And you will notice that this is, so I'll just make a punchline here. Alpha here was -1 and beta here was 2, right? And so the alpha goes here and the beta goes here and here. So the -1 goes here and the 2 goes here. So in general, this is the punchline. If you have a imaginary roots, your alpha will go here and your beta will go here and here. But your solution form would look like t raised to the alpha times C1 cosine of beta ln of t plus C2 sine of beta ln of t. Our problem up here, alpha was -1 and beta was 2, so that's why those numbers are there. But if they were some others, they'd go in these spots. So again, this is like probably what you'll write on your formula sheet. It looks different than the one we had before because there's these ln's of t's and stuff. And then instead of e to the alpha t, it's t to the alpha. But this comes from all this work here. And then I skipped and reused stuff from last time to get this. But you don't have to know the derivation. You just need to know this. But it would be nice to know where it came from. So earlier when I scheduled that test, I didn't realize that we don't have class on Friday, and so people might want to come on, might have wanted to come to office hours on Friday, but people, I mean, I can still hold my office hours on Friday, but people may not be in town and people might be traveling. So I'll send out a poll for people who want to maybe push the test later in the week. So I'll just make the choice either Monday, Wednesday, or Friday. You can still vote for Monday if you want to have it on Monday, but I know some people might be traveling or have other Easter commitments. So we could push it to Wednesday or Friday, and then I'll have my office hours, during the week. So like if people couldn't come on Friday's office hours and want to go through some review, we could do that on Monday, Tuesday, Wednesday, depending on what day everybody wants to take the test. I could still hold office hours this Friday. Yeah, I mean, even like at a time that's better for you guys or the same time that I usually do it. Yeah, I can still do that. I think I'm gonna just keep it a one-parter, so I'll make it like just long enough that not too much so that you can do it in one period. Because if we do a two-parter, it eats into another class period, and we've got like variation parameters, reduction of order, Laplace transforms, linear systems of differential equations, a phase plane. There's a lot of topics, and I don't want to rush coverage. So I'll just write a test that I know is enough for me to measure how well you know second order equations, and just like be okay with one day's worth of problems is enough for me to get a good idea of whether you know it or don't know it at some level. I can't sacrifice another class period, but it could be on any of the days next week. I'll just send a poll later today, so you guys can vote on that. But I'm still around, so I'm not going out of town. So if people need help during Friday and the weekend, I'll be.
Thank you.
Yeah.
Us.